here we are again. So I'm going to turn it over to John now for the continuing series on chromatic quasisymmetric functions.
Thanks very much. I assume this is the last one, and so I would like to thank Anne and Jim again for inviting Michelle and me. It's been a great pleasure for me to talk to some old friends and some people I've never met. And, this is a terrific thing. I thought about what I should talk about, and this was very difficult. I sought a little advice from colleagues and ignored it. This, for me, it's not true for Michelle. Her amazing work with Anders Björner on shellability is more cited than our joint paper here, but this is my most cited paper. And so there are many things that I could have chosen, and I chose a few, and we'll see how many I can talk about. I'd like to talk about two in some detail and then maybe mention some more recent results. So in fact, the first thing I want to talk about is not really a recent development, and it's almost as old as our work, and some of it predates our work. And this is the work, oops, that didn't work at all.
You have to share screen.
Yeah, I'm not shared. There we go. There, good. This is the work of Clearman, Hyatt, Shelton, and Scandera from 2015. And this relates the chromatic quasisymmetric functions to Heck algebra characters. And this is not at all surprising in some way that a relationship exists, because the chromatic quasisymmetric functions arose from our efforts to understand Stembridge's immanent conjectures. And in fact, Heyman had used Heck algebra characters to attack Stembridge's immanent conjectures in the 1990s or early 2000s. And so one of the upshots of this beautiful work is that the graded Stanley-Stembridge conjecture of Michelle and myself is in fact a special case of a more general conjecture of Heyman, which of course remains open. So you know, I don't know who knows what, so let me remind you about the type A Heck algebra. Right, so this is, sorry, the ground ring. The ring of Laurent polynomials in Q to the 1/2 for some Q, right? With generators. Well, I'll call them TI or TSI. And here one is less than or equal to I, less than or equal to n-1. And in fact, SI is an element of the symmetric group. It's the transposition I plus 1. So you have one generator for each adjacent transposition, right? And now the relations, right, is given by a presentation. Ti squared is Q minus 1 Ti, right, plus Q T1, right? So this is the identity element, multiplicative identity element, which corresponds to the identity element of the symmetric group, right? And Ti, Tj, Ti is Tj, Ti, Tj if the absolute value of I minus j is 1, and Ti, Tj is Tj, Ti, right, if I minus j in absolute value is larger than 1. Okay, so if you stare at these are essentially the same relations satisfied by the SI in the symmetric group. Right, these are just the braid and commutation relations for the adjacent transpositions in the symmetric group. And if Q is 1, right, this in fact just says that Ti squared is the identity. So if Q is 1, This is nothing but the group algebra over this particular ring, I guess over the integers, if we set Q to be 1, right, of the symmetric group. And in general, if you substitute a generic complex number for Q, in fact, you get the group algebra of the symmetric group. If you substitute 0 or a non-trivial root of unity, you get something else. In any case, these are very useful in studying representations of symmetric groups and general linear groups over finite fields and so on and so forth. And the next observation, this is all well known and can be found in many places in the literature. Say we take a reduced word, as I don't know, SI1, SIL, right, is a reduced word. That means it's just as short as possible in SN, right? We define TW is by definition TI1, TIL. And the content of this is it doesn't depend on the reduced word, right? There are many ways to write a permutation as a product of adjacent transpositions, using as few transpositions as possible. And these relations here guarantee that this is well defined, right? And now these TWs, right, is a basis for this Heck algebra, which I should have given a name earlier, HNQ. Okay. All right. But there's another basis that turns out to be very interesting and important. This is the Kazdan-Lustig basis. Okay, and so I'll write CW prime, C prime sub W, right? And so here W runs through SN, Q, I'll explain this notation in a second, and it'll kind of go away later. And you sum over all the V's that live below W in the Bruja order. In other words, some reduced word for V is a subword of some reduced word for W. Some polynomial in Q, TV. These are called Kazdan-Lustig polynomials. And these are very, very interesting, but they aren't really the subject of this talk. So these are just some things that exist. This basis here of C primes has many nice properties that the sort of obvious basis of T did not. And let me just say that Q of VW is a power here if V lives below W in the Bruja order. Okay, so this is the setup, and of course this is just scratching the surface, but this Kazdan-Lustig theory is extremely interesting, to say the least. Has generated a lot of really good work by wonderful combinatorialists and algebraists, and it's a fascinating thing. So now what does this have to do with what we're doing? Well, these authors here define a bijection from the set of 3, 1, 2 avoiding permutations this is, sorry, oh, that's very bad. This is in bijection with Hessenberg vectors. We call it, I don't know, B, right? With the following property. This gives a relation, and I'm going to put some more simple. So the first thing I want to, so 3, 1, 2 avoiding means if I read W in one line notation, there aren't three symbols, they're not necessarily adjacent, right? If I read W in one line notation, I cannot find three symbols anywhere in the sequence such that the biggest one is first, the smallest one is second, and the middle one is third, right? And now, right, let's say I want to take, well, I like to write it after applying the involution, but I'm going to write the chromatic quasisymmetric function of one of these unit interval graphs. So I call my bijection B. There's W, right? So this, from my permutation W, I get a Hessenberg vector, right? This tells me a unit interval graph, as in the previous lectures. And I look at the chromatic quasisymmetric function. I apply the involution. It exchanges the H and E's. And let me respect the authors of the paper and use Q, where Michelle and I use T. And here it makes some sense because we're going to relate to Heck algebras where it's standard to call the parameter Q. And now, I'm going to write some gibberish, and then I'm going to explain what the gibberish is. So this is some Greek letter. This sum is over all partitions lambda of n. And now I'm going to take this Kazdan-Lustig basis element, and it got normalized by dividing by a power of q, and I'm going to unnormalize it. So this Kazdan-Lustig basis element is nothing but the sum of all the standard basis elements over v's that live below w in the Bruja order and weighted by these Kazdan-Lustig polynomials. Right? So we don't know what those are. And now I'm going to put m lambda here. So m lambda is sort of the most natural way to write a quasi-chromatic symmetric function, although we've applied the omega. So this is really telling us how to write the chromatic quasi-symmetric function, the original chromatic quasi-symmetric function, in terms of the so-called forgotten symmetric functions, the images of the m's under the involution. So what's this? This is a character value, right? So, just like the group algebra or the group Sn itself, this Heck algebra has representations. This is the Q analog of the representation whose Frobenius characteristic is the H lambda, the complete homogeneous symmetric function. So let me write this down in some way. So H lambda of Q is a parabolic subalgebra of Hn of Q. And let me just define it by example. So say I have the partition 3, 3, 2, right? Then H lambda of Q generated by T1, T2, T4, T5, and T7, right? Just like the parabolic subgroup of the symmetric group Sn will be generated by the first two reflections. That gives me S1, 2, 3. Skip the third reflection. The next two reflections, that gives me the symmetric group on 4, 5, 6. And this last thing gives me the symmetric group on 7, 8. So we just set up the Q analog. We get some subalgebra, right? And then what is this induced character, right? So character is just a trace function. This thing is the character or the trace function of, well, a one-dimensional representation of this subalgebra, right? So this W here will live in this subgroup S3 cross S3 cross S2. And now if Q were 1, we would take the trivial representation, right? But in Q land, what we do is just take the length function, right? This is a perfectly good homomorphism from this algebra, right, to, if you like, 1-by-1 matrices with coefficients in the ground ring. All right. This is just like this is a Q analog of the trivial representation, and now we want to induce up And I mean, this is just some notation for inducing it up. Right. So if Q were 1, this is nothing but the permutation representation of on cosets of some parabolic subgroup, or if you prefer, on ordered set partitions of this shape. Right. But now there's a Q involved, so you get this length character, you take this length representation, parabolic subalgebra, and you induce it up to the whole algebra. That's what this stands for, if you remember, graduate algebra, right? So what this theorem says is we can write this chromatic symmetric function in terms of, or the adjusted chromatic symmetric function, in terms of the monomial characters or symmetric functions, right? By evaluating, right? This W tells us a particular chromatic symmetric function. I'll tell you what this is. Well, I'll tell you a different version of this bijection shortly. And basically says we can determine this symmetric function by evaluating the analog of the H lambdas, or if you like, in modules, this is what's called big M upper lambda in Bruce's book, right? This is just the Q analog. We evaluated at a particular Kazdan-Lustig basis element, and that tells us the coefficients of the M's in here. And I should remark, and I think I'll write down another one shortly after I explain to you ways to understand this bijection. I'll write something in terms of the E's, because what we're or in the H's, I guess, because I've applied omega, right? We're really interested in this thing here being H positive, right? And these character values here are polynomials in Q, and we would like them, therefore, right, to be polynomials with non-negative integer coefficients if I replace these particular polynomials by something that has the H's here. But I wanted to start this way, right, that the representations from which you extract irreducible representations tell you how to write this in terms of the monomial symmetric functions. They have formulas for every basis, and the Hecke algebra characters might become virtual characters, right? But they manage this. So this, I think, is very, very interesting. And in fact, so let me tell you my way of understanding this bijection. It's not what they write. They introduce some objects called descending star networks, and they use these descending star networks to get a bijection like this. I want to tell you a simple bijection that Ryan Schneider and I discovered when Ryan was an undergraduate here. And then I want to tell you that Nate Lesnovich, who's a grad student here, pointed out to me, although I haven't confirmed, that it's even simpler than that. So we want to go from 3-1-2 avoiding permutations to Hessenberg vectors. And the first thing I want to do, for me, the intermediary is the poset of positive roots. So I would again like to show you this by example, right? So in between Hessenberg vectors and 3-1-2 avoiding permutations are ideals in the poset of positive roots. So I'm just going to do the case where n is 4 or n is 3, depending how you want to say it. All right, here are the positive roots in type A. Right, and this is the positive root poset, right? One root lives above another if their difference is in fact a non-negative sum of simple roots, is a root. Sorry, is a non-negative sum of simple roots. And now I would like to, I'm going to sort of put a linear extension, well, not a linear extension, a linear order. So the way I'm going to pick roots from an ideal is to first go up this line, then go up this line, and then go up this line where there's nothing to go up. All right. And now let me just randomly pick an ideal. Here's an ideal in the poset of positive roots. It's closed downward. Okay. So what I want to say is this corresponds to both a Hessenberg vector and a 3-1-2 avoiding permutation. And the Hessenberg vector, I just look and basically see every one of these roots corresponds to a potential edge in the complete graph. And if I choose such edges, I'm going to get a Hessenberg graph. So I can draw, if you prefer, the Hessenberg graph. I have 1, 2, I have 2, 3, right? I have 3, 4, and I have 2, 4. And so the Hessenberg vector, I mean, really, this is the graph I'm going to use here, is nothing but 2, 4, 4, 4. And now I would like to get a permutation, and certainly each of these roots corresponds to a reflection, a transposition across the, a reflection across the orthogonal hyperplane. And so I would like to take a product of the reflections corresponding to this roots, and this blue scheme here tells me in what order to do it. This, then this if it were here, but it's not, then this, then this if it were here, and then this. And so now I should write, and I'm going to multiply permutations left to right. This is one of the reasons Michelle is one of my very favorite co-authors, that she does not insist that I do it the other way. Right, and so I'm going to multiply left to right. This is the 3-cycle 1, 2, 4, and in one line notation, this is 2, 4, 3, 1, which is most certainly 3, 1, 2, 3. So this is the bijection. All right. E of 2, 4, 3, 1 is 2, 4, 4, 4. This is not what's in the paper. This is, as I said, Ryan, who's now a grad student at UCSD. Right? And I discovered that this is the same as what's presented. But Nate pointed out to me, let me take this Hessenberg space here.
John?
Go ahead, Teddy.
Yeah. Is there a canonical choice for the blue order?
Is there a
canonical choice for the blue order? Is it canonical?
This is a very good question, and I think the answer is probably no. Right, and I used to know. I can't remember what goes wrong if you try and go, the other way, like this, and then this. Right, something happens if you try and go this way. There might be very many other orders. This one mimics the Clearman-Hyatt-Scandera, Shelton-Scandera bijection, and then that's why we chose this one. But I believe there are others. Right, and maybe if you go this way, instead you have to use 2, 3, 1 free rather than 3, 1, 2 free, and it turns out that will probably not cause much trouble for the kind of things that we're doing. It's a good question, and I used to know more about it, but I believe the answer is no. You can, there are other, well, of course, there are many bijections as soon as you have one, but I think there are other reasonably organized bijections that you could choose.
Thank you.
Sure. So here, right, for 2, 4, 4, 4, here's the Hessenberg space. And Nate points out to me that, well, right, here's the permutation 2, 4, 3, 1, which the permutation matrix fits inside the Hessenberg space. And in fact, this is the longest permutation whose matrix fits inside the Hessenberg space. And Nate tells me that, in fact, this is a more succinct way to present what was presented in the paper and what I presented to you here. In any case, the upshot of this is that there's a bijection, right? And that we have, well, not we, they have a beautiful theorem like this that says, in fact, the chromatic quasisymmetric function is determined by these Heck algebra characters evaluated at unnormalized Kazdan-Lustig basis elements, right? I mean, it's a little strange to do this, but this suits our purposes, and the normalization suits most other purposes. Okay. So let me write down another version, because this gets at the Stanley-Stembridge conjecture. So I always like to I'm going to write it in terms of the H's, right? And so, all right, Let me make one remark. These Heck algebra characters, they are Q analogs of the symmetric group characters, and the transitions, let me check the chat to see if I've missed a. It's the bijection, I don't know, different from taking minimal dict path that contains ones in the given permutation matrix. No, that's what it is. That's another way of saying it. Thank you, Jason. If Nate is right, which I think he is. Okay. So let's write it in terms of the H's, and I want to say that there are transition matrices between the standard bases for symmetric functions, and therefore that tell you how to get from various standard looking sets of virtual characters to others, right? And these are the same in Q land. And so this is actually a virtual character. I'll tell you what it is in a second. Phi lambda Q. This again is over all permutations. Okay. So what's this? This is the Q analog, the Heck algebra version of, the Frobenius characteristic of the monomial symmetric function. So this is not an actual character, or if when Q is 1, you don't get an actual character of Sn, you get a virtual character. And this is a trace function, and it's not the trace function of an actual representation, it's the trace function of a virtual representation. Sorry, did you have a question? Okay. Right, so this is some Q analog of a virtual character, and this tells you, the evaluating here tells you the coefficients of the complete homogeneous symmetric functions, and the graded Stanley-Stembridge conjecture just says that for every lambda, this here is a polynomial with non-negative coefficients. This is the graded version of the Stanley-Stembridge conjecture that Michel and I introduced, right? If and only if each Q lambda Q E W C prime W, right? For every W and for every lambda, right? These are polynomials. That's not in question. Right? These will definitely be polynomials, right? The issue is whether their coefficients are not negative. Right? And so, in fact, because of this theorem of Kleeman, Hyatt, Shelton, Scandera, it turns out that the graded Stanley-Stembridge conjecture is a special case of a conjecture of Heyman. Of course, we didn't know that when we developed this conjecture, and this is not trivial, right? So this is interesting. Where did I put this? Heyman conjectured in 1993 that this thing, right? So here for the graded Stanley-Stembridge conjecture, we're allowed, right? We're assuming that W is 312 avoiding, right? Heyman conjectured that this thing here that we're interested in sorry. That this thing here is for all lambda and all W in Sn. So that's more general, right? We only need the 312 avoiding W's to prove the graded Stanley-Stembridge, right? So this is of course, an open conjecture of Heyman's, and so I like this setup a lot, this paper, because it ties everything back together. Heyman pointed out that this conjecture here implies Stenbridge immanent conjecture, or at least part of it. Right? And so this theorem of Clearman, Hyatt, Shelton, Scandera ties everything back together. And you know, this is a beautiful and interesting conjecture. So unless someone has comments or questions, I'd like to change the subject. Great. So there are connections to algebra and there are connections to geometry. I'd like to show you some sort of slightly different geometry. What we learned, right, that the results of Brosnan and Chow and the other proof of Matthew IPAC, right, says, as Michelle and I conjectured, that this chromatic quasisymmetric function, right, is the Frobenius characteristic of a representation on cohomology of a certain manifold, namely a regular semi-simple Hessenberg variety. So there's another setup of the same type. And the characters just change. So here again, M, right, we have a Hessenberg vector. And now we have this graph, the Hessenberg graph, right? So this says that we have edges from 1 to all the vertices up to M1 and so on and so forth, the incomparability graph of natural unit interval order, right? And now the chromatic symmetric function and the graded version that Michelle and I introduced deals with proper colorings of this graph. Right, that's what you deal with, but you could look at all colorings. So I called K the set of all proper colorings. And so A is just a set of all integer colorings of V. So all functions, kappa, right, V to the positive integers. Right, so now we don't worry if the coloring's proper, right? And then I want to write, this is, I don't think, standard notation at all. Right, LM, I'm going to go back to T, right, is the sum over all colorings, not just the proper ones, of the same thing. You can define a sense. Here, a sense are strict. If two vertices that are joined by an edge get the same color, that doesn't count as an ascent, right? And now x to the kappa, the monomial, right, the product of x, right, V, as usual. So this looks just like the chromatic symmetric function, except it's not chromatic, right? You just take all the functions. So let's just quickly look at some example. 3, sorry, here I am, 2, 3, 3, right? And so I want to claim, right, this is M3 plus what? 1 plus 2t M21, right, plus 1 plus 4t plus t squared M111. Okay, why is this true? So this says I use one color 3 times. That's what this 3 says. There's no ascents. I can just, I use one color, I put it everywhere, there's no ascents. So there's no powers of t to be seen. I just get M3. Here I use one color twice and the other once, right? So if I put the largest color here, there are no ascents. That's this. If I put the largest color in either of these two places, there's one ascent. That's this, right? If I put a 5 here and a 7 here and a 5 here, I get one ascent from 5 to 7, right? Here, I'm using all the colors 1, 2, 3. That's a proper coloring, and this is the same answer we had before, right? We are counting ascents in a permutation, right? And we get the Eulerian polynomial, right? And in fact, right, this is what? S3 plus 2t S21 plus t squared S111. And if you're familiar with this kind of stuff, you see that this is a grading of the regular representation of S3. The one-dimensional representations or characters appeared once each. The two-dimensional character appeared twice. And in fact, what this is a unicellular LLT polynomial. So LLT stands for La School Clerk Tibon, unless someone wants to correct me. These are of considerable interest in representation theory and algebra, and recently in the kind of in algebraic combinatorics that's done by many of you, right? And so let me remark, these are studied by Carlson Mellett in work on the shuffle conjecture. Right, and by Jim and Andy. Okay. Any experts who wish to make comments now are welcome to about this whole setup. Why is this symmetric? It's a great question, because it is. I'll tell you why in just a second. This is a great question because it's not obvious to me that it has to be symmetric, but it is. And now I'll tell you why, because I'll tell you a result that I think you can find in Carlson Mellett, not stated this way, and you can find explicitly in the work of Jim and Andy, right? Which is that these are related by plethism. Hopefully I won't misprint here. And now I believe I should do something like this kind of plethism here. So some kind of plethistic substitution into something we've already proved to be symmetric gives this L here, and therefore it's symmetric, right? Is this okay, Jim, or have I mangled it?
Yeah, that is the quickest way to prove it, given that you've already proved the chi-G is symmetric.
Great. All right. Is it obvious that this should be symmetric?
No, that's takes a little bit of proving. There's a combinatorial proof due to Mark Heyman and his student Michelle Byland in the appendix of our JAMS paper on the McDonald formula. That's probably the simplest proof, direct proof. It has a lot of elements in common with your proof that the chi-G is symmetric.
I see. Thank you. I didn't know. And thanks for the question. You know, I would have just jumped
John,
over it.
before you move on, in the quasi-symmetric case, the latter part is, coefficients are Eulerian. Is there anything known about the coefficients, the other coefficients?
I believe the answer to that is yes, but it's going to depend on M, right? For certain sort of, I don't know what the right word is, you know, at the end of this sort of interval of functions, these are well-known things of Hessenberg vectors, right? If you have n, or 1, 2 up to n, these are well known. In the middle, I don't know formulas for sure expansion, although certainly you can extract from here because we know, right? And so, for instance, if you want in terms of the p's, right, then it's straightforward to go back and forth because you're doing plethism, right? I don't know how to quickly write down formulas for s's, but I believe this has been studied and stuff is known.
Okay, thank you.
Sure. It's a good question. Sorry, I don't have a better answer at my fingertips. So what I'd like to show you is some recent work which gives the same kind of geometric setup, right? So these things here are Frobenius characteristics of action on symmetric group of cohomology of some manifold, right? And this action, one way anyhow that you can get this action is using this GKM theory, right? These manifolds emit a nice action of a torus. And these manifolds have what are called twins by the people who discovered this setup, who are Anton Eisenberg. And these are submanifolds of the flag manifold, and they look so much like the regular semi-simple Hessenberg varieties that it's natural to think they're the same. They aren't. They share many very nice properties, and as we'll see, you can get the LLP polynomials. This is recent work. There are preprints and not published papers. So the first thing is we want to realize the space of flags is slightly different. Instead of using the general linear group and the Borel subgroup, we use the, this is a compact torus. So the unitary group is compact, right? These are matrices A such that A conjugate transpose is the identity, right? So this is the unitary group, and this sits inside the general linear group, the n by n general linear group. And its intersection with the diagonal torus, right, it consists of things on the unit circle in the complex plane. So I'm going to call this T, even though it's a different T than the old T. And the idea is that, in fact, the general linear group is transitive on the usual flags, and the stabilizer of a particular flag is the Borel subgroup. The unitary group remains transitive on flags, and now the stabilizer is just this torus here, right? And so this is just a different coset model for the flag variety, right? And now I want to say that UN acts by conjugation on the space of Hermitian matrices. Right. So that just means that X is, sorry if I'm insulting you by reminding you of these facts, right? And so if I conjugate a Hermitian matrix by unitary matrix, I get another Hermitian matrix, right? And so what we're going to do is pick a generic orbit. And I'm going to take a regular semi-simple element, and we're over the complexes, but we want some unitary matrix like this. I'm sorry, some Hermitian matrix, right? This is most certainly satisfies this condition. It's its own transpose, and there's no bars to be found, right? And we consider, right, the UN orbit of S. Right, so we just conjugate S everywhere we can by unitary matrices, and what I want to observe is, well, certainly this is a set on which UN acts transitively, right? And what's the stabilizer of S? It's all unitary matrices that commute with S, but commuting with S, because S is regular semi-simple like this, means you're diagonal, and that's T. Every diagonal matrix in UN is one of these here, right? Right, so this thing here is nothing but the flag manifold, right? Because it looks like this, right? And now we want to cut things out, right? And all you do, right? Given, let me give this a name, S to the UN, right? So that's the flag manifold, right? So now we're given a Hessenberg vector. Right, and now I'm going to call this AB for Eisenberg Buchstaber, right? This is all matrices, or all cosets, sorry, GT, right, flags, with the property that G inverse SG is in what I want to call the unitary Hessenberg space for M. And what does this look like? Right. Well, the way we get a regular Hessenberg space, right, from a Hessenberg vector is to force some zeros. And now we just force the mirror zeros, right? We just do like this. Right. So the matrix here, right, Aij, if I have a matrix Aij, it's 0 if I is greater than Mj or J is greater than Mi. Hopefully I didn't mangle that. You know, right, you cut from top and bottom, right? Because you have this relation, you know what you're getting is Hermitian. So in fact, you could actually say it lives in the Hessenberg space. This is in some way extraneous because I know this matrix is Hermitian, satisfies this condition. So if I live in the Hessenberg space, I actually live in the unitary Hessenberg space, whatever you want to call this. Okay. So these were studied by Eisenberg and Buchstaber, and I mean, they are in spirit very, very much like the regular simple Hessenberg varieties. And so here are some theorems. Right. This really, I guess, depends on S and M, but they have the same Betty numbers. They have the same, but they're not always homeomorphic. Certainly not always isomorphic as manifolds or varieties or whatever. T acts on this Buchstaber manifold, and GKM theory applies. Right? So the same story I told you a couple of weeks ago, right, can be told here. The GKM graphs as graphs for these are isomorphic, but the edge labels are different. So I'd like to show you an example when M is 2, 3, 3, because that's the example I always use. So we have these vertices labeled by permutations, all right, like before. And we used to label the edges by which numbers were exchanged, right? This edge would be labeled E1 minus E3. And if you remember, the ordinary and equivariant cohomology rings are determined by assigning polynomials at the vertices so that differences across edges are divisible by edge labels. But here we're going to label by positions. So here we have T1 minus T2, T2 minus T3. What's this? T1 minus T2. Right. T2 minus T3, T1 minus T2, T2 minus T3. And now we have the same rules, right? So maybe what could we assign? Let's look at some legal assignment, right? I don't know, maybe 0, T1 minus T2, T1 minus T3. I'm probably going to mangle this. T2 minus T3, right? 0, 0. this should work, right?
John, I
then-
think that 231 at the bottom, that should be 21.
Oh, that
Right.
absolutely should be 213. Thank you. Shall. Yeah, that's just a misprint, not a mistake. Right. And now I would like an SN action on cohomology the same way. So maybe I would apply the permutation 1, 2, right? And now if I apply the permutation 1, 2 here, I'm going to have a mess. It's not going to work, right? This would become T1 minus T3. I'd put it here and I'd put the 0 here and I would be out of luck. So I don't bother, or they don't bother, or anyone who thinks of this doesn't bother applying SN to the indices, just to the graph, right? And then you will see T2 minus T3, right? T1 minus T3, T1 minus T2, 0, 0, 0. And unless I've mangled it, this is legal. And so this gives an action of SN on the cohomology of the Eisenberg-Buchstaber manifold, right? So this is some dot action, right? And now I'd like to tell you a theorem, and this is a recent theorem, right? There's a paper in progress or a preprint, I forget which it is, by Martha Prekup and Eric Summers. And there's a recent archive posting, Masuda and Sato. The Frobenius characteristic for the dot action, I'll keep calling this the dot action, on H star, and the cohomology of this Eisenberg-Buchstaber manifold is nothing but the LLT polynomial. This actually unpublished conjecture of Andy and myself, but here are the people who actually proved it. And this, and I should remark, certainly Makia did not know. I don't think that I had this conjecture. I forget if Martha did or not, but this is due to them and not to Andy and myself. So I think this is a beautiful theorem. You know, this says that this whole circle of ideas and methodology is broader than we thought. Right? All these two things I showed you, right? That what Michelle and I discovered is the tip of what I think is an interesting, well, iceberg. I don't know how big it is and how deep it is, but that there are other things like this sitting out there, and there's more to be discovered. Okay, I have a few minutes left. Let me maybe just mention shortly some progress, right? Because so where do we stand? I can say when Michelle and I first started and made this conjecture about the chromatic quasisymmetric function being the Frobenius characteristic for the dot action, we thought that the hard part was going to be to prove this conjecture. Once you knew that, and it was hard, right? If you look at the Brosnan-Chow proof or the Gay-Paquet proof, they aren't easy at all. We kind of thought that would be the tough part. But in fact, the graded Stanley-Sembridge conjecture remains open. There's not a ton of progress in using this connection to geometry to solve the combinatorial problem. Let me just mention some, and I would say this is fairly mild. I mean, it's nice work, but we're not too far. So here's a theorem of Megumi Harada and Martha Prekup. I should say our goal was to get the combinatorials interested in geometry. I think we succeeded better at getting geometers interested in combinatorics. Graded Stanley-Sembridge conjecture. This is not how they say it. This is how I say it. It's equivalent. This, GM has no independent set of size 3. So it's a pretty dense graph, right? This is a start. And, you know, maybe it's not so much, but you have to start somewhere, right? And this they do with considerable force. There are other ways to do it, maybe, but they're not so easy. This has been improved, was improved, Sujin Cho, Jae-Yoon Hung. Same for no independent set of size 4. They talk in terms of bounce numbers. I mean, the language in these papers is not the same, but you can interpret it this way. As far as I know, this is as far as the method. This is technical, real, both of them, right? Require some amount of technique. These are not sort of easy things to do. Let me check. Bruce is right. This is what Megumi and Martha call the abelian case. What this means is you have the Hessenberg space. You could look at its complement, right? So in the lower left corner, you're forced to put zeros. You could put anything northeast, but you could just take the complementary matrix where the zeros are forced in the northeast and the free entries are in the southwest. And given a Hessenberg vector, this thing will be an ideal in the Borel subalgebra of lower triangular matrices, right, in the Lie algebra of the linear group, right? And this no independent set of size 3 exactly means that this ideal is abelian, right? If you bracket two matrices whose non-zero entries are concentrated in the southwest, right, you'll get some lower triangular matrix again, and this condition is equivalent that when you bracket any two such matrices, you get 0. Right, that's the condition on GM. So that's correct. Thanks, Bruce. And there was
John?
Philippe said so. Sorry, your question was answered before I started talking. Thanks to both of you.
Yeah, Dan, since you raised up this unitary Heisenberg matrices where you forced corner zeros in the southwest and northeast, what happened, and is totally curiosity, what happens if you force zeros in each of the 4 corners?
I have no idea. It might, so if you force too many zeros, you might be restricting the rank, right? You have to be careful how you force them, right? And then you'll want to start working with nilpotent matrices, which is very, very interesting, right? But not sort of related to combinatorics in the same way. I have no idea. I would assume, right? So if you cut out a small piece, then you're not necessarily restricting the rank, depending on how you cut it. I have no idea what happens. I should say, I believe in work of Eisenberg, Buchstaber, they look at other graphs, right? These forced zeros, right? You could just think of as coming from a graph, and they look at other graphs besides Hessenberg graphs. But I don't know whether or not they look at arbitrary graphs, but you might look there. They have a different paper on the subject, or several papers on the subject, and you might want to look at one that doesn't have the title Hessenberg varieties in it, and then they might have something to say.
Thank you.
Sure. Let's see, what else do we know? Well, instead of restricting the graph, right, this is a graded right, conjecture about a whole bunch of cohomology groups. So you could just look at some of them. This was also, Tim knew this and Michelle and I knew this, but the sort of nicest explanation is in this paper here, right? So this is Sujin Cho and Jae-Yoon Hung and Yoon-Jung Lee. And right, H2. If I just look at the second cohomology group, the graded Stanley-Sembridge conjecture holds just in degree 2. All right, that's known. So that's some progress. There are reasons for this. The irreducibles that appear in H2 are very restricted. They have 2 rows, and therefore, right, it's sort of straightforward and right say what an H positive symmetric function is when the irreducibles appearing are 2-row irreducibles. Right? They're just straightforward, but their version is a nice geometric version which gives some hope of getting further. These versions here are just sort of force, combinatorial force, and they're less interesting because it's not clear how to extend H4 and H6 and so on. Right? Oh, sorry, I see I'm over time. I had a few others I just wanted to mention in passing, but I don't want to go on because I'm not going to give you any insight. You know, you can see on MassSciNet a decent number of papers that have our paper as a reference. Look at them. So I apologize to anybody who's here who I didn't mention, and maybe the people who are not here who I didn't mention. There's a lot of interesting work, and this is just what I chose. So thanks again very much for your attention. It's been a great pleasure for me.
All right. Well, thank John. And so did I take it right then? This is your last talk, John? Or
Yeah,
okay.
I'm out of town for the next.
Okay. Well, let's thank both John and Michelle for a great series here. That was really fantastic. And I think now we'll be taking a break from IPAC for 2 weeks. Our next talk is 2 weeks from today, and Anna will be giving a series of 3 talks on the latest and the greatest in this series of kind of dynamic papers by the Blasiak, Heyman, Morse, Poon, Seelinger group. McDonald polynomial operators, diagonal covariant algebras, and the combinatorics of Dick-Paz. Okay, any final questions for John or Michelle or whatever?
I have a question about the next series of talks. So I can wait, or I can ask right away.
Go ahead.
What should one do to prepare for the series of talks?
Oh, you don't have to prepare anything. I'm going to, don't worry about it. I'm going to just probably was focus on more on the combinatorial interpretation, and because all my notes are already online, so you can always read it afterwards if you're interested. So yeah, you don't have to prepare for anything.
All right, great. Thank you.
That sounds like we got a real vacation for 2 weeks then.
I have a question for John.
Sure.
So is there a way to see the plothistic relationship between the LLT polynomials and the chromatic quasisymmetric functions using the ABM module? Can you see it from the representation?
That's a great question, because you could ask about other types and if there's an AB set up in other types. And so those different GKM graphs, if you look in Matthew's paper, right, basically what's going on is that these things are modules over the polynomial ring, right? There's assignments to the GKM graph, but there's 2 versions of the polynomial ring that act. Right, and the difference between the edge labels, right, can be interpreted that way, and probably that should explain the plethism, but I can't do it. I think I make too many mistakes when I think about plethism, and I would expect that in fact the answer is yes, and that if you look in Matthew's paper, he's got, although he doesn't expound on it at all, he's got something about the non-chromatic quasi-symmetric function using the Hopf algebras and so on. So there's probably some story that explains all of this and likely allows some kind of generalization to other lead types, which I think would be really interesting, but, you know, I have not done it. So I think it might be worth pursuing.
Maybe I can ask, do you know the recent geometric work, if that sheds any light on like other LLT polynomials like strips, which are also sure positive?
Not that I know of. I don't know what's in the work of Martha and Eric. I don't know all of what's in the work of Martha and Eric, and so you could ask them. I don't know.
Any other questions? It's not, okay. We'll have a happy July 4th weekend. And see you in a few weeks. So long.
Thank you.
Bye.
Thank you.
Thank
Anna.
you. Safe travel.
Thanks.
Thank
Thank
you.
Bye.
Bye.
Thank you.
Bye.
Everybody.